Because if you wanted to try and visualize what would this look like, one way that you could is you could think of space-time as the surface of a still pond. And you drop a big rock in the middle, and there's a wave that travels, a ripple that travels on the surface. It travels outwards from where you drop the rock. And if you were a little teeny tiny ant on a surfboard, you would surf that wave, right?
And the wavelength, so the distance between the crests,
right,
would be related to how big was the rock that you dropped in.
Exactly, right.
Okay. So when you measure gravitational waves with LIGO or whatever other tools available to you, you try to measure the wavelength of that so that you can infer what created that wave. Because otherwise, you didn't see the thing happen.
No, exactly right. So we measure a number of things. We measure the wavelength, which is the spacing between the peaks, in the successive peaks. We also measure the amplitude, which is how big, what was the height of the wave. And both of those things are changing with time, depending on what the source is. So by measuring sort of the shape of the wave,
as you go into it and as you come out of it.
As it passes by you.
Yeah, as it washes over the earth.
Exactly. And as you do that, you can you can infer some of the properties of the system that emitted that wave. Sort of like if you just saw the ripple at the edge of the pond, and you have to kind of measure the frequency of the wave, you have to measure the amplitude of the wave, you have to know something about the density or the viscosity of the water of the pond.
Well, that's right, because the medium, it would come through differently.
Right. And once you have put those things together, without ever seeing the rock fall in the center of the pond, you can say something about the rock.